Space is full of mysteries, and today we're diving into one of the most fascinating ones: sounds from deep space. Over the years, scientists have discovered some bizarre noises coming from the far reaches of our universe. These aren't just random signals, they're actual sounds recorded by NASA and other space missions, captured from planets, moons, and distant galaxies. In this video, we'll explore 10 mysterious sounds that have puzzled scientists. 1. Sound beyond the Kuiper Belt. In the vastness of space, where even light takes years to reach distant stars, there are parts of our solar system that remain relatively unexplored. One of the most remote and mysterious regions is the Kuiper Belt. This is a vast band of icy bodies, dwarf planets, and other celestial debris that stretches out beyond Neptune, far beyond the orbit of the outermost planets. The Kuiper Belt is often described as the final frontier in our solar system, a region filled with relics from the early solar system that could hold the keys to understanding how the planets were formed. NASA's Voyager 1, launched in 1977, is the farthest human-made object from Earth. After studying Jupiter and Saturn, it ventured into interstellar space, crossing the solar system's boundary beyond the Kuiper Belt. There, it detected a unique hum caused by electromagnetic plasma waves, which are oscillations in magnetic fields generated by interactions between solar wind and sparse plasma, charged particles like protons and electrons. Voyager 1's Plasma Wave Science (US) detector recorded these high-frequency waves inaudible to humans and converted them into audible tones through frequency modulation. The resulting sound, a steady, low hum, offered the first auditory glimpse into the interstellar environment. By analyzing the wave density, velocity, and frequency, scientists gained groundbreaking insights into the behavior of plasma and the dynamic interactions between the solar wind and interstellar medium, advancing our understanding of this distant, uncharted region of space. NASA's transformation of these high-frequency waves into audible sounds preserved their structure, offering a snapshot of the plasma environment at the edge of the solar system. These sounds were not random, but reflected complex solar wind and plasma interactions, revealing the physics of interstellar space and marking a milestone in our exploration of the universe's outermost boundaries. The sound captured by Voyager 1 wasn't just an interesting oddity. It was a scientific breakthrough that helped us understand the space environment more intimately. Voyager 1's journey into interstellar space was not just about observing the distant stars, but also about uncovering the intricate, invisible sounds of the universe itself. If you think this captured sound was mind-blowing, then you're not ready for what's next. 2. UFO on the Moon. Apollo 11.
We have some explanation for that. We have none. Don't worry. Continue your program. Oh boy, it is. Roger, we know about that. Did you go the other way? No, let's the other way. No, that's kind of rich. Very spectacular. God, what is that there? That's hollow. What the hell is that? Don't tangle. It's kind of light there now. Roger, we got it. We marked it. Lose communication. Almost tangle. What? Here's the bell. Here's the bell. Yeah. But this is unbelievable.
The Apollo 11 mission, launched on July 16, 1969, remains one of the most monumental achievements in human history. It marked the first time humans set foot on the moon, with astronauts Neil Armstrong and Buzz Aldrin making history by walking on the lunar surface. The mission was watched by millions around the world and symbolized the peak of space exploration during the Cold War-era space race. However, a lesser-known event took place during this historic mission that has fueled speculation, intrigue, and conspiracy theories for decades: an alleged UFO sighting. The story begins when the Apollo 11 astronauts are in lunar orbit and preparing for the historic moon landing. During their communications with NASA's mission control, the astronauts reported something unusual: strange noises or signals that were not easily explained. These noises were picked up by NASA's listening stations and became a point of interest. Armstrong and Aldrin were heard on live transmission discussing what they believed to be an unidentified flying object near their spacecraft. During Apollo 11, astronauts Neil Armstrong and Buzz Aldrin reported seeing a distant light near their spacecraft and hearing an unusual high-pitched rhythmic sound while in lunar orbit. Aldrin described the light as moving strangely, and Armstrong noted the sound as distinct from regular radio or mechanical noise. NASA's Tracking and Data Relay Satellites, TDRS, captured the sound, which faded before the lunar landing. NASA attributed these phenomena to radio interference and technical glitches, but the lack of a definitive explanation, coupled with lost or unreleased tapes, fueled speculation. The incident sparked widespread interest, with some theorizing extraterrestrial involvement. Critics questioned NASA's conclusions and pointed to inconsistencies in the evidence. Despite official explanations, the event remains unresolved, becoming a key part of Apollo 11's legacy and an enduring subject of debate among researchers and the public. The Apollo 11 UFO incident remains a compelling mystery in space exploration history. Despite NASA attributing the strange sounds and UFO sighting to radio interference and technical errors, their lack of transparency and missing recordings have fueled doubts and conspiracy theories. Some believe NASA withheld details to prevent panic or protect sensitive information about possible alien contact. The unexplained nature of the event, combined with astronaut Edgar Mitchell's suggestions about extraterrestrial life, has sustained public fascination. While no definitive proof links the incident to alien activity, it continues to spark debates and intrigue, symbolizing humanity's enduring curiosity about the possibility of life beyond Earth. Let's now look at the fascinating sound of Jupiter's magnetic field. Jupiter, the largest planet in our solar system, has long captivated scientists due to its massive size, intricate storms, and powerful magnetic field. Unlike Earth's magnetic field, which is relatively modest in comparison, Jupiter's field is immense, intense, and far-reaching. It extends millions of kilometers into space, creating a magnetic environment that's both alien and awe-inspiring. The discovery of Jupiter's magnetic field dates back to the early 1970s, when NASA's Pioneer 10 and Pioneer 11 spacecraft made their flybys of the gas giant. They provided the first measurements of Jupiter's magnetic environment, revealing that it was far more powerful than anyone had anticipated. However, it wasn't until Voyager 1 and Voyager 2 passed by the planet in the 1980s that scientists gained a deeper understanding of the field's structure and complexity. These spacecraft found that Jupiter's magnetosphere, the region controlled by its magnetic field, was not only vast, but also unlike anything seen around other planets in the solar system. NASA's Juno mission, launched in 2011, has provided groundbreaking insights into Jupiter's magnetic field. Using the WAVES instrument, Juno recorded decometric radio emissions, a form of electromagnetic waves generated by the interaction of charged particles with Jupiter's powerful magnetic field. These waves, created by particles from Jupiter's moons and solar wind spiraling along magnetic field lines, were converted into eerie, audible sounds like whistles, chirps, and hums. Jupiter's magnetic field, caused by its rapid rotation and metallic hydrogen core, extends far into space, shaping its magnetosphere and interacting with solar winds to produce intense radiation belts. The sounds vary based on factors like solar activity and charged particle density, offering a dynamic soundscape of Jupiter's magnetosphere. During solar storms, emissions become stronger, altering the sound's intensity and frequency. These recordings are more than auditory phenomena. They provide critical data on Jupiter's magnetic structure, radiation belts, and solar wind interactions. They also help scientists monitor changes in the magnetosphere, revealing how Jupiter's magnetic influence affects its moons and surrounding environment. This research deepens our understanding of one of the solar system's most dynamic regions. Jupiter's magnetosphere, one of the largest and most powerful structures in the solar system, generates strange sounds through its interactions with charged particles. This magnetic field, 20,000 times stronger than Earth's, is powered by Jupiter's rapid rotation and metallic hydrogen core, which acts as a dynamo, converting kinetic energy into electromagnetic energy. The sounds are actually decometric radio emissions, DEM, electromagnetic waves produced when high-energy electrons spiral along magnetic field lines and accelerate through regions of varying magnetic intensity. Particles from sources like the solar wind and Jupiter's volcanic moon Io interact with the magnetosphere, causing these emissions. As electrons spiral through stronger magnetic regions, they emit radio waves at low frequencies, which Juno's Waves instrument records and shifts into audible tones. The resulting sounds, whistles, hums, and chirps, are dynamic, varying with particle density and magnetic strength. Jupiter's intense radiation belts and solar activity, such as coronal mass ejections, CMEs, amplify these emissions, creating an evolving soundscape. These sounds, influenced by universal patterns in magnetic field interactions, not only reveal the mechanics of Jupiter's magnetosphere, but also provide a comparative understanding of magnetic phenomena across planetary systems. Have you ever heard of a sound called NGC 2392, which shocked the whole world? Let's take a look at it. NGC 2392, commonly known as the Clown-Face Nebula, is a visually captivating planetary nebula located approximately 4,000 light-years from Earth in the constellation Gemini. Its nickname comes from its unique appearance, which, through a telescope, resembles a clown's face, a bright central region surrounded by a colorful ring of gas and dust. This nebula represents the final stages of a dying star's life, specifically a star similar to our Sun, which has ejected its outer layers into space as it approaches the end of its life cycle. Planetary nebulae like NGC 2392, the Clown-Face Nebula, form when a dying star sheds its outer layers, leaving a white dwarf core that emits ultraviolet radiation. This radiation ionizes surrounding gases, creating colorful patterns influenced by elements like hydrogen and oxygen. NGC 2392 offers valuable data on stellar death and nebular composition. Recent advancements have enabled scientists to transform the nebula's electromagnetic signals, such as radio waves and X-rays, into audible sounds through sonification. Instruments like NASA's Chandra X-ray Observatory and Hubble Space Telescope capture these emissions and map them into frequencies perceivable by the human ear. The resulting sounds, eerie pulses and chirps, reflect the nebula's structure and activity. High-pitched tones signify fast-moving gases energized by ultraviolet radiation, while lower-pitched sounds indicate cooler, denser regions with slower-moving gas. This sonification process provides a novel way to study NGC 2392's dynamic processes, enriching our understanding of stellar evolution and offering an immersive sensory experience of the universe's intricacies. These sounds map the nebula's velocity and density distribution, allowing researchers to trace its expansion and track its transformation over time. Additionally, the patterns and frequencies in the sonified data reveal the chemical composition of the nebula, indicating the presence of elements like hydrogen, oxygen, and nitrogen. This innovative approach enhances our understanding of stellar evolution, offering a multi-dimensional perspective on the life cycle of planetary nebula like NGC 2392. But what if I told you that it has produced a sound, and our scientists have captured it? The Perseus cluster is one of the most massive and extensively studied galaxy clusters in the universe, situated approximately 250 million light-years away in the constellation Perseus. It hosts thousands of galaxies, immense quantities of hot gas, and a central supermassive black hole that significantly influences the cluster's overall dynamics. This colossal gravitationally bound system spans an enormous region of space, with its matter heated to extreme temperatures of millions of degrees, making it a fascinating subject for astrophysical research. At the core of this immense cluster lies a supermassive black hole with a mass millions of times greater than that of the Sun. This black hole is not only the largest object within the cluster, but also the origin of a remarkable phenomenon: sound. The Perseus cluster's supermassive black hole produces an eerie, low-frequency hum, resulting from pressure waves propagating through the hot gas surrounding it. In space, sound doesn't travel as it does on Earth due to the vacuum, but the dense medium of hot gas and plasma in the Perseus cluster allows these pressure waves, akin to sound waves, to ripple outward. These waves are generated by the immense gravitational pull of the black hole compressing the surrounding gas, creating fluctuations in pressure. Detected by NASA's Chandra X-ray Observatory in 2003, these waves vibrate at ultra-low frequencies, approximately 57 octaves below middle C, far below human hearing. Scientists translated these inaudible frequencies into a range perceptible to the human ear, revealing a haunting, organ-like tone. This transformation enables us to hear the interactions between the black hole and its environment, providing a unique sensory perspective on its cosmic influence. This discovery underscores the power and complexity of supermassive black holes, offering valuable insights into how they shape the galaxies and cosmic structures around them. It serves as a reminder of the universe's vast mysteries and the innovative methods used to uncover them. When converted into audible frequencies, the pressure waves generated by the Perseus cluster's supermassive black hole produce a steady musical hum. This sound reflects the black hole's immense gravitational influence, which stirs surrounding gas, releasing energy and creating shock waves. These pressure waves ripple through the hot ionized hydrogen gas at the cluster's center, forming vibrations akin to waves spreading across a pond. As matter spirals into the black hole during accretion, the energy released compresses and expands the surrounding gas, generating pressure waves. These waves oscillate on a timescale of millions of years, corresponding to a frequency about 57 octaves below middle C, far below human hearing. By translating these frequencies into the audible range, scientists transform these cosmic vibrations into sounds that provide valuable insights. This wrath of a black hole sound reveals the dynamic interactions between black holes and galaxy clusters, offering a unique glimpse into the processes shaping these colossal cosmic structures. Through the study of these pressure waves, researchers deepen their understanding of galaxy cluster evolution and the role of black holes in the universe's architecture. Astronomers at NASA, using data from the Chandra X-ray Observatory, successfully detected the pressure waves as X-ray emissions originating from the hot gas surrounding the supermassive black hole. These emissions were then converted into sound waves audible to humans by mapping the pressure fluctuations to higher frequencies within the human hearing range. These low-frequency sounds serve as a powerful tool for studying the intricate gas dynamics around black holes. What's more shocking than this was the sound captured by one of the Jupiter's moon. 6. Io moon. Io, one of Jupiter's many moons, stands out as the most volcanically active body in our solar system. With over 400 active volcanoes, this sulfur-covered moon is constantly reshaped by eruptions that spew molten lava, gas, and sulfur dioxide. This extreme volcanic activity also drives one of the most fascinating phenomena in space: the generation of radio emissions that can be interpreted as sound. But how does volcanic activity lead to sound in the vacuum of space? The answer lies in the interaction between Io and Jupiter's immense magnetosphere. Jupiter's magnetic field is exceptionally powerful, stretching far beyond the planet and influencing the behavior of its nearby moons, including Io. As Io orbits Jupiter, it becomes an active participant in the creation of a plasma torus, a ring of charged particles encircling the planet. This torus forms from the gas and dust ejected during Io's volcanic eruptions, which become ionized and trapped within Jupiter's magnetic field. This dynamic interaction generates electromagnetic waves that can be converted into audible frequencies, creating a soundscape tied to Io's volcanic activity and its relationship with Jupiter's magnetosphere. Io's volcanic eruptions play a critical role in the Jovian system by producing gases and particles that interact with Jupiter's powerful magnetic field. When ionized particles from Io's eruptions enter the plasma torus, a vast ring of charged particles encircling Jupiter. They spiral along the planet's magnetic field lines, generating electromagnetic activity. This process produces decametric radio emissions, DAM, which spacecraft like NASA's Juno and Galileo missions have detected and converted into audible sounds. The plasma torus, formed from Io's ejected sulfur dioxide and other volcanic materials, is a dynamic and energetic region influenced by Jupiter's magnetic field. As charged particles in the torus accelerate and decelerate, they emit radio waves that vary in intensity and frequency. These emissions reflect the density, velocity, and energy of the particles within the torus, offering valuable insights into Jupiter's magnetosphere and its interaction with Io's volcanic activity. When transformed into sound waves, these radio emissions provide a unique auditory perspective on the high-energy processes at work. Io's volcanic activity fuels the plasma torus and drives electromagnetic interactions, making it a central player in understanding the dynamics of Jupiter's magnetosphere, space weather, and the Moon-planet relationship. These sounds not only captivate, but also deepen our understanding of the Jovian system. The sounds generated by Io's interaction with Jupiter's magnetic field offer a fascinating auditory glimpse into its dynamic environment. As Io's volcanic material interacts with Jupiter's powerful magnetosphere, charged particles create radio emissions that spacecraft detect and convert into audible frequencies. These emissions range from low-frequency whistles to high-pitched buzzing tones, reflecting the energy levels of particles, magnetic field strength, and plasma wave activity. When translated into sound, the emissions mimic natural and familiar earthly noises, whistling wind, humming, or buzzing machinery. This auditory resemblance arises from the behavior of electromagnetic waves, which propagate through space and are processed into decametric waves below 30 MHz. These moaning, whistling, and buzzing sounds vividly illustrate the dynamic and ever-changing nature of Io's plasma torus. The frequency and intensity of the sounds shift with Io's volcanic activity. Increased eruptions alter the ion density in the plasma torus, producing variations in pitch and amplitude that audibly echo Io's volcanic landscape. These sounds provide a unique tool for studying the interplay between Io's eruptions, Jupiter's magnetic field, and the Jovian system's energetic processes. Saturn, a planet that is known for its beauty, but not people are aware that there can be deadly lightning strikes, and the scientists have managed to capture it. Saturn, the second largest planet in our solar system, is known for its magnificent ring system. The planet also boasts an atmosphere teeming with violent storms and chaotic weather patterns. Among Saturn's most fascinating phenomena are its lightning strikes, which erupt deep within its thick cloud layers. These storms are not only extraordinarily powerful, but also far more extreme than anything witnessed on Earth. Saturn's atmosphere is primarily composed of hydrogen and helium, with trace amounts of gases such as methane. Beneath its dense cloud cover, where temperatures can plummet to a frigid 180 degrees to 290 degrees, massive electrical storms form. These storms generate lightning bolts that are up to 1,000 times more powerful than those on Earth. This intense lightning activity highlights Saturn's turbulent weather, with storm systems so vast they can span the entire planet, offering a striking example of the planet's dynamic and volatile nature. Saturn's lightning is a striking phenomenon, occurring within immense, long-lasting storm systems that dwarf Earth's thunderstorms. These storms, like the Great Storm of 2010, can span the entire hemisphere and persist for months, producing lightning so powerful it illuminates the planet and generates radio waves detectable from space. NASA's Cassini spacecraft, which orbited Saturn from 2004 to 2017, captured these radio emissions using its radio and plasma wave science instrument, converting them into audible sounds. Unlike Earth's lightning, Saturn's discharges occur under unique atmospheric conditions, creating electromagnetic waves of distinct frequencies and strengths. These waves ripple through space, where Cassini intercepted and recorded them. The ARS instrument transformed the signals into sound, allowing scientists to hear Saturn's storms and gain valuable insights into the planet's atmospheric dynamics and magnetic interactions. This discovery marked a milestone in planetary science, offering a sensory perspective on Saturn's extreme weather. The data revealed the scale and intensity of Saturn's lightning, providing a deeper understanding of storm dynamics and advancing our knowledge of its complex atmospheric and magnetic systems. The sounds of Saturn's lightning, recorded by NASA's Cassini spacecraft, offer a rare auditory glimpse into the planet's colossal storms. Using its radio and plasma wave science instrument, Cassini detected high-frequency radio emissions from Saturn's lightning and shifted them into the audible range. The resulting sounds are crackling and eerie, reminiscent of static electricity or faint thunder, providing an auditory voice to Saturn's dynamic weather systems. These crackles and pulses are not only captivating, but also scientifically revealing. The pitch and intensity of the sounds correspond to the frequency and strength of the radio waves. High-pitched bursts indicate strong electrical discharges, while lower frequency tones reflect weaker or more distant events. The variations in sound mirror the storm's size, altitude, and intensity, as well as the composition of Saturn's atmosphere. By analyzing these sounds, scientists gain insights into Saturn's storm structure and electrical activity, including the interaction between its weather and magnetic environment. Cassini's recordings revealed prolonged, intricate bursts of electromagnetic energy unique to Saturn's lightning, offering a dynamic and evolving soundscape. These auditory observations enrich our understanding of planetary atmospheres and demonstrate the immense power of Saturn's storms, connecting us to a distant world in an unprecedented way. 8. Eagle Nebula. The Eagle Nebula, or M16, is among the most iconic and visually striking regions in space, situated approximately 7,000 light-years from Earth in the constellation Serpens. This stellar nursery is a vast expanse of gas and dust where new stars are born. The nebula's most famous feature is the Pillars of Creation, towering columns of gas and dust immortalized by stunning images captured by the Hubble Space Telescope. Beyond its breathtaking beauty, the Eagle Nebula serves as a critical site for astronomers studying the life cycle of stars, as it offers a unique window into the process of star formation from the remnants of older stellar generations. The Eagle Nebula, a vast star-forming region within a massive molecular cloud, emits powerful electromagnetic signals due to its dynamic processes, such as star formation and supernova remnants. While space lacks the atmosphere to carry traditional sound waves, instruments like the Chandra X-ray Observatory and Hubble Space Telescope capture these signals, including X-rays and radio waves. Scientists then use sonification to transform this data into audible frequencies, creating a sensory representation of cosmic activity. The sounds of the Eagle Nebula, described as structured hums and high-pitched tones, reflect its energetic processes. High-pitched tones correspond to hotter, more active regions, such as those near the iconic Pillars of Creation, where new stars form. Lower-pitched sounds indicate cooler, less active areas. These variations provide a sonic fingerprint of the nebula, revealing information about gas temperature, density, and energy dynamics. X-rays from the hot gases, particularly near the Pillars of Creation, were converted into audible frequencies in 2001, producing distinct humming tones. This breakthrough offers scientists insights into the physical conditions within the nebula, such as the intensity of star formation and interactions within the interstellar medium. By transforming electromagnetic signals into sound, researchers have developed a groundbreaking way to study and experience the universe, making the Eagle Nebula's extraordinary processes both informative and evocative. 9. Venus Surface. In the early 1960s, the Soviet Union went on an ambitious Venera program, aiming to unravel the mysteries of Venus, a planet renowned for its enigmatic atmosphere and extreme conditions. This series of space missions sought to land spacecraft on Venus and transmit groundbreaking data back to Earth. The program's primary goals included studying the planet's surface and atmospheric composition, offering unprecedented insights into one of the most hostile environments in our solar system. Among the most notable missions in this program were Venera 13 and Venera 14, launched in 1982. The Soviet Venera 13 and 14 missions achieved groundbreaking success by capturing the first-ever sound recordings from the surface of Venus, providing a rare auditory glimpse into one of the solar system's most hostile environments. These landers, equipped with advanced technology, endured Venus's extreme conditions, temperatures of 465 degrees, 869 degrees, atmospheric pressures, 90 times that of Earth, and corrosive sulfuric acid clouds. Despite their brief operational lifespans, the landers transmitted invaluable data, including the sounds of Venus's turbulent surface. The recordings revealed low-frequency hums caused by high-speed winds, consistent with atmospheric currents reaching speeds of 400 km/h, 250 mph. These winds produce a relentless storm-like roar, much more intense than anything experienced on Earth. The landers also captured sounds during touchdown, where the vibrations from their interaction with Venus's rocky surface were converted into low-frequency noise, providing a direct auditory record of spacecraft descent and landing. Mechanical noises from the lander's systems, such as cooling mechanisms and electrical components, were also evident. These sounds reflected the lander's resilience in Venus's extreme heat and crushing pressure, showcasing the sophistication of the Venera program. The auditory data enriched scientific understanding of Venus's atmosphere and surface dynamics, marking a significant achievement in planetary exploration. 10. Rings of Uranus. The discovery of the sounds produced by Uranus's rings represents a fascinating milestone in solar system exploration. Unlike Saturn's iconic rings, the rings of Uranus remained largely enigmatic until NASA's Voyager 2 spacecraft conducted its historic flyby in 1986. This mission provided the first in-depth data about Uranus, including its rings, moons, and magnetosphere. Among the suite of scientific instruments aboard Voyager 2 was the Plasma Wave Science instrument, designed to detect electromagnetic waves in the form of radio frequencies. These waves are generated by the interaction of charged particles with planetary magnetic fields and plasma environments, such as those found around Uranus and its rings. As Voyager 2 passed through Uranus's magnetosphere, its Plasma Wave Science instrument captured radio signals from the planet's rings, later transformed into eerie, high-pitched whistles and buzzes. These electromagnetic waves, originating from interactions between Uranus's magnetic field, charged particles, and the icy and rocky debris of the rings, offer a unique auditory glimpse into the planet's dynamic environment. Uranus's rings interact electrostatically with the surrounding plasma and magnetic field, generating radio emissions that reflect the energy levels of particles within the system. High-pitched tones correspond to energetic particles, while lower frequencies indicate less dynamic interactions. The sounds exhibit rapid oscillations, rhythmic pulses, and dips in intensity, highlighting the dynamic forces shaping the magnetosphere. The recordings also reveal patterns of resonance, where particle oscillations align with Uranus's magnetic waves, creating repetitive acoustic features. These space sounds resemble radio emissions from auroras on Earth and other gas giants, but are uniquely influenced by the icy composition of Uranus's rings. 11. Pulsar stars. Pulsars are highly magnetized neutron stars, remnants of massive stars that collapsed in supernova explosions. These dense objects, no larger than a city, rotate rapidly, emitting beams of electromagnetic radiation from their magnetic poles. When these beams align with Earth during rotation, they produce detectable signals, giving pulsars their characteristic pulsing nature. The sound of a pulsar is not a direct audio phenomenon. Instead, it is the result of electromagnetic signals, primarily in the radio spectrum, detected by radio telescopes. These signals are then converted into audible frequencies for analysis and demonstration. This process translates the timing of the pulsar's emissions into rhythmic, periodic sounds, often resembling steady ticks, chirps, or beats. Each pulsar has a unique frequency, determined by its rotation period, which ranges from milliseconds to seconds. For example, the Crab pulsar, located in the remnants of a supernova observed in 1054 AD, emits signals at an astonishing rate of 30 times per second. When converted into sound, this pulsar produces a rapid, rhythmic beat akin to a drumming pattern. Similarly, millisecond pulsars, spinning hundreds of times per second, create high-frequency sounds reminiscent of a buzzing or whirring motor. The precise timing of these sounds underscores pulsars' role as cosmic clocks. Scientists study these signals to understand extreme physics, including the behavior of matter in ultra-dense conditions, gravitational waves, and tests of Einstein's theory of general relativity. Notably, pulsars have also been used to map gravitational anomalies in space, contributing to our understanding of cosmic structure. Each pulsar tells a story of violent stellar death and intricate cosmic mechanics. The sounds they produce are a testament to the universe's complexity, providing both a haunting and mesmerizing insight into the remnants of ancient stars. 12. Orion Nebula. Deep in the constellation of Orion, a stellar nursery glows with ethereal beauty, the Orion Nebula. This vast region of gas and dust, over 300 light-years away, is a cradle for new stars, where cosmic forces shape the universe's youngest celestial bodies. But while its visual splendor is well known, scientists have also explored the sound of the Orion Nebula, translating its phenomena into a new sensory experience. The sound of the Orion Nebula isn't a direct auditory signal. Instead, it's a result of data collected through telescopes being converted into audible frequencies. This process, called sonification, transforms light wavelengths, density variations, and other measurable characteristics into sound waves, creating a music of the cosmos. In the case of the Orion Nebula, scientists map the spectrum of light emitted by its gases and stars, assigning specific tones to different colors or intensities of light. When these data are converted, the Orion Nebula's sound tells a mesmerizing story. The deep, resonant hums represent clouds of hydrogen gas, the building blocks of stars. Higher, flute-like tones capture the energetic bursts of young stars releasing ultraviolet radiation. Occasionally, faint crackling or shimmering sounds represent the chaotic interactions of dust and gas being pulled together by gravity, painting a vivid auditory picture of star formation in progress. The Orion Nebula's soundscape educates us about its complexity and structure. By listening to this stellar nursery, we gain insights into the interplay of elements that form stars and planets. The sonified data can also make astronomy accessible to a broader audience, including those with visual impairments, allowing more people to experience the wonder of space in a new, immersive way. 13. Milky Way Galaxy. The Milky Way, our vast spiral galaxy, is often thought of as silent, an expanse of stars, planets, and dark matter quietly orbiting its center. But in the scientific realm, the sound of the Milky Way is not the type you hear with your ears. It's a translation of invisible phenomena into frequencies we can experience. Through this transformation, the galaxy reveals an auditory dimension to its existence, providing a unique way to understand its structure and activity. The sound of the Milky Way is derived from radio waves, electromagnetic signals, and vibrations in interstellar material. These waves, captured by instruments like radio telescopes, are converted into sound waves we can hear. This process, called sonification, allows scientists and even artists to translate raw data into audio. It's an approach that turns the movement of celestial bodies, the energy of star formation, and the patterns of cosmic radiation into tones, pitches, and rhythms. One of the most intriguing examples comes from the galactic center, home to the supermassive black hole Sagittarius A. This bustling region is packed with activity, stars circling at incredible speeds, gas clouds colliding, and magnetic fields twisting. When data from this region is sonified, the result is a deep, rumbling sound, interspersed with higher-pitched whistles and crackles. These variations reflect the energy and chaos of the Milky Way's heart. Moving outward, the galaxy's spiral arms, brimming with young stars and star-forming regions, offer a different auditory experience. Their sound is more rhythmic and harmonious, representing the organized motion of stars and gas within the gravitational embrace of the galaxy. Even the faint whispers of cosmic microwave background radiation, a relic of the Big Bang, can be converted into a subtle, haunting hum, serving as a reminder of the Milky Way's origins. Sonification not only helps scientists interpret complex astronomical data, but also invites the public to engage with the cosmos in a new and immersive way. By listening to the Milky Way's voice, we gain a deeper appreciation for the dynamic forces that shape our galaxy. It's a reminder that even in the quietest corners of the universe, there's a symphony of activity waiting to be discovered. 14. Cat Eyes Nebula. Cat's Eye Nebula, officially known as NGC 6543, is a stunning cosmic formation located about 3,300 light-years from Earth in the constellation Draco. Its intricate and symmetrical patterns, resembling a feline eye, have captivated astronomers and casual stargazers alike. But beyond its visual beauty, this nebula has a fascinating sound that tells a story of stellar death and rebirth. This sound is not something the nebula inherently produces, as space is a vacuum where sound waves cannot travel. Instead, scientists create these sounds through a process called data sonification. In the case of the Cat's Eye Nebula, data from telescopes capturing the nebula's light, energy, and structure are converted into musical notes or sound waves. Each frequency or pitch corresponds to a particular wavelength of light or a specific feature within the nebula, such as regions of gas or dust. The result is an eerie and harmonious representation of the nebula. Low, droning tones often symbolize cooler gas regions, while higher, sharper pitches reflect areas of intense radiation or hot, ionized gas. The Cat's Eye Nebula's soundscape becomes a symphony of the cosmos, where each note tells a part of the story of its central star shedding its outer layers in the final stages of its life. The nebula's formation, visible as intricate rings, bubbles, and filaments of gas, is a product of stellar winds and intense radiation sculpting the expelled material. Over thousands of years, these forces created the nebula's mesmerizing, layered structure. When sonified, these physical features transform into a detailed audio experience, offering listeners a new way to engage with the universe. What makes the Cat's Eye Nebula sound so educational and intriguing is how it bridges science and art. It allows audiences to hear the life cycle of a star, its violent ejections of gas, its cooling phases, and the complex interaction of forces shaping its surroundings. 15. Horsehead Nebula. The Horsehead Nebula, an iconic cloud of gas and dust in the Orion constellation, is a striking sight for astronomers. Its name comes from its distinct shape, resembling the head of a horse, sculpted by stellar winds and radiation from nearby stars. But what does this celestial masterpiece sound like, while space itself is silent? Due to the absence of a medium for sound waves to travel, scientists have found a creative way to interpret the nebula's voice using sonification. Sonification is the process of converting astronomical data, such as light intensity, wavelength, or chemical composition, into sound. In the case of the Horsehead Nebula, this involves translating the nebula's visual features and energy patterns into audible frequencies. By assigning specific tones to the brightness of stars, the density of gas clouds, and the presence of certain elements like hydrogen and carbon monoxide, researchers craft an auditory representation of this majestic region of space. Listening to the Horsehead Nebula is like hearing the symphony of its structure. The dense, shadowy regions of gas produce low, deep hums, while the radiant ionized zones emit higher-pitched tones. Nearby stars, whose energy shapes the nebula, contribute rhythmic pulses or sparkling notes. Together, these elements create a soundscape that mirrors the nebula's dynamic interaction of light, matter, and energy. The storytelling aspect deepens when you consider the forces at play. The Horsehead Nebula is part of the vast Orion Molecular Cloud Complex, a stellar nursery where new stars are born. As radiation from massive stars erodes the nebula's dense material, it not only shapes the iconic silhouette, but also ignites processes that will one day form new celestial objects. The sonification captures this transformative process, reminding us that the universe is alive with activity, even in its most tranquil-looking regions. For many, hearing these cosmic sounds bridges the gap between science and art, making the vastness of space more tangible. It's an innovative way to connect with phenomena that are otherwise inaccessible to our senses, turning distant light years into something we can experience right here on Earth. 16. Karen P. standing in the vastness of space, listening for the whispers of celestial bodies. Among these whispers lies the sound of a moon orbiting a dwarf planet, a phenomenon that, while not directly audible, becomes a symphony of signals when interpreted by scientific instruments. To understand this, we must first explore what creates these sounds. Dwarf planets like Pluto or Haumea often have moons that accompany them on their journey through the cosmos. These moons, locked in a delicate gravitational dance with their parent body, are dynamic and interactive objects. But in the vacuum of space, sound as we know it cannot travel. Instead, we rely on electromagnetic signals or vibrational data to interpret what we perceive as sound. The story begins with the interaction between the moon and its surroundings. Some moons, like Pluto's Charon, are geologically active or have icy surfaces and tenuous atmospheres that can interact with solar wind, a stream of charged particles emitted by the sun. This interaction generates electromagnetic waves, which, when detected by spacecraft, can be translated into frequencies audible to the human ear. These signals often resemble ethereal, wavering tones or pulsating hums, akin to nature's ambient music. For instance, NASA's missions have recorded the sounds of moons in our solar system. These aren't actual sounds, but the transformation of collected data into auditory formats. Vibrations from tidal forces, interactions with magnetic fields, or even the moon's atmosphere contribute to these signals. Each moon tells its own tale through its distinct frequencies. Consider the possible soundscape of a moon like Charon. As it orbits Pluto, tidal stresses may create vibrations within its icy crust, sending faint ripples of energy into space. If Charon had any magnetic activity, it could generate electromagnetic songs, similar to the eerie sounds recorded around Jupiter's volcanic moon, Io. These sonifications, when processed, could produce haunting, wavering tones that echo the moon's slow dance around its dwarf planet. These sounds aren't just a novelty, they hold scientific significance. By listening to a moon's voice, scientists can learn about its composition, surface activity, and interactions with its parent dwarf planet and the solar environment. Such data enriches our understanding of celestial mechanics and the diversity of objects in our solar system. 17. Uranus moons. Uranus and its moons drift in silence, at least to human ears. But silence is deceptive. These moons, with their icy crusts and mysterious interiors, may speak in ways we are only beginning to understand, revealing their secrets through electromagnetic signals converted into sound. The story begins with Uranus itself, a giant ice planet tilted dramatically on its side, its magnetic field wildly misaligned with its rotation. This creates an unusual and dynamic environment for its moons: Ariel, Umbriel, Titania, Oberon, and Miranda, among others. As these moons move through Uranus's magnetosphere, they interact with charged particles in a process that generates waves of energy. These waves, though invisible and inaudible to us directly, can be detected by spacecraft instruments. The sounds associated with Uranus's moons are a product of data gathered from these interactions. NASA's Voyager 2 spacecraft, which flew past Uranus in 1986, detected plasma waves and variations in magnetic fields caused by the movement of charged particles near the moons. These raw electromagnetic signals were later converted into audio frequencies, producing haunting, otherworldly sounds. Imagine a deep hum punctuated by rising and falling tones, like the slow breath of an ancient being. These sounds are not only mesmerizing, but also profoundly informative. They hint at the dynamic interplay between the moons and Uranus's magnetosphere. For example, the data suggested that some moons, like Miranda, may have subsurface oceans or cryovolcanic activity. These features could explain the disturbances in the surrounding plasma waves. The tones captured from these moons vary. Some suggest gentle rhythmic pulses, akin to waves lapping at an alien shore. Others hint at sharp bursts of energy, perhaps indicating the presence of complex magnetic interactions or geysers ejecting material into space. Scientists listen carefully to these sounds, seeking clues about the composition, structure, and activity on these enigmatic moons. Through these sounds, we begin to imagine the unseen: icy surfaces cracking under tidal stress, subsurface oceans sloshing beneath thick crusts, and magnetic fields whispering secrets of geological activity. Uranus's moons may seem frozen and distant, but their voices bring them closer, making them vivid and alive in our imaginations. 18. Ida's moon. In the vast expanse of the asteroid belt between Mars and Jupiter lies Ida, a small and rocky asteroid that, at first glance, appears unremarkable. Yet in 1993, during NASA's Galileo spacecraft mission, astronomers made a discovery that changed how we think about these seemingly isolated celestial bodies. Ida, it turned out, was not alone. Orbiting this asteroid was a tiny companion, later named Dactyl. This discovery marked a historic milestone. Dactyl became the first moon ever identified orbiting an asteroid. Unlike pulsars, which emit electromagnetic waves that can be translated directly into rhythmic patterns, Ida and Dactyl don't produce sounds in space. However, scientists can use a fascinating technique called sonification to convert their data, such as their movements, interactions, and physical characteristics, into audio. Through this process, we can imagine what the sound of Ida and Dactyl might reveal about their unique bond and shared history. Picture Ida, an asteroid with a rugged and uneven surface, slowly rotating in the silence of space. Dactyl, a tiny moon no wider than a mile, faithfully orbits its larger companion at a distance of about 90 kilometers. Scientists can measure its orbital speed, distance, and gravitational effects on Ida. When this data is translated into sound, Ida's slow rotation might be represented as a steady, deep hum, a constant rhythm in the cosmic void. Meanwhile, Dactyl's swift and slightly irregular orbit could create lighter, higher-pitched tones, producing a dynamic melody that mirrors its journey around Ida. Together, these tones form a celestial duet, offering a glimpse into their orbital dance. But the story of Ida and Dactyl doesn't end there. Both bodies are believed to be fragments of a much larger asteroid, shattered billions of years ago in a violent collision. Their surfaces are scarred with craters, each marking an ancient impact. If this history were sonified, we might hear sporadic drum beats, sharp and sudden sounds, each one echoing a collision that shaped their current forms. These auditory elements would tell a tale of destruction and survival, a history etched into the very rocks of Ida and Dactyl. Sonification isn't just an artistic endeavor. It's also a powerful educational tool. By turning complex astronomical data into sound, scientists can uncover patterns and details that might otherwise go unnoticed. For instance, subtle changes in Dactyl's orbit caused by Ida's irregular gravitational pull could be translated into slight shifts in pitch, revealing insights into the asteroid's mass distribution and internal structure. This auditory approach also makes astronomy more accessible to visually impaired individuals, allowing them to explore the universe in a way that transcends sight. The sound of Ida's moon, Dactyl, is more than a scientific curiosity. It's a reminder of how humanity connects to the cosmos. By transforming cold, hard data into something we can hear and feel, science creates a bridge between the distant universe and our personal experiences. 19. Phobos, Mars. The red planet has two small moons named Phobos and Deimos. They are much smaller than Earth's moon and have irregular shapes like big lumpy rocks. Scientists think they might be captured asteroids from space, which makes them unique and fascinating to study. But have you ever wondered what their sounds might be like? Of course, these moons don't actually make sounds we can hear. Instead, scientists use special tools on spacecraft to measure things like their movements, vibrations, and interactions with Mars. Then, they convert that data into sounds so we can better understand these mysterious moons. Phobos, the larger moon, is incredibly close to Mars, only about 6,000 kilometers above the planet's surface. That's closer than any other moon in our solar system. It orbits Mars very quickly, completing a trip around the planet in just over 7 hours. If its motion were turned into sound, it might be like a deep, steady hum or a drum beat that repeats quickly. But there's more to Phobos' story. It's being pulled so strongly by Mars's gravity that it's slowly breaking apart. In the distant future, Phobos might completely disintegrate and form a ring around Mars. Deimos, the smaller moon, is much farther away from Mars, at about 23,000 kilometers. It takes longer to orbit, around 30 hours for one complete trip. If its motion were converted into sound, it might feel softer and more distant, like a calm, slow rhythm. Unlike Phobos, Deimos isn't under as much stress from Mars's gravity, so it's more stable and peaceful. 20. Saturn's moon. Amid the magnificent rings of Saturn lies one of the most fascinating moons in our solar system, Pan. Shaped like a flying saucer, this tiny celestial body measures just 35 kilometers across, but it plays a crucial role in the structure of Saturn's rings. Pan orbits within the Encke Gap, a 325-kilometer wide division in Saturn's A ring, and its gravitational influence keeps this gap clear of ring particles. While Pan doesn't produce sounds in the traditional sense, scientists have found ways to interpret its movements and interactions through sound using sonification. To imagine Pan's sound, we first need to understand how sound in space works, or rather, doesn't work. Space is a vacuum, which means there are no air molecules to carry sound waves. But scientists can convert data about Pan, its motion, gravitational interactions, and even its peculiar surface features, into audio. By translating numerical data into sound, they create a way for us to hear Pan's story. Pan's orbit around Saturn is a rhythmic, predictable journey. If this motion were turned into sound, it might resemble a steady, low-pitched hum, symbolizing its consistent path through the Encke Gap. But Pan isn't just gliding silently through space, it's actively sculpting its surroundings. As the moon moves, its gravity acts like a cosmic plow, pulling and scattering nearby ring particles. This interaction could be represented as softer, intermittent tones overlaying the hum, creating a soundscape that reflects the balance of Pan's influence and its harmonious relationship with Saturn's rings. Pan's unique shape, often compared to a ravioli or flying saucer, also adds to its story. The ridges around its equator were likely formed as ring material accumulated over time. If these surface features were sonified, we might imagine sporadic drum beats or tapping sounds, representing the collisions and accretions that shape the moon's structure. Each sound would symbolize a moment in Pan's long history of interacting with Saturn's rings. Beyond its physical characteristics, Pan's soundscape could tell the story of its creation. Scientists believe Pan formed from the same material as Saturn's rings, gradually growing as it collected debris. This origin might be represented by a rising tone, symbolizing the gradual buildup of the moon over millions of years. Sonification of Pan's data isn't just a creative exercise, it's a powerful scientific tool. By listening to variations in sound, researchers can identify subtle patterns in Pan's interactions with the rings, such as how its gravity affects the distribution of particles. These soundscapes also make space exploration more accessible, allowing people of all abilities to experience the wonders of the cosmos. 21. Triton. Far out in the distant reaches of our solar system lies Neptune, the icy giant wrapped in intense blue hues. Orbiting this mysterious planet is Triton, a moon unlike any other. Triton is not just Neptune's largest moon, it's unique because it orbits in the opposite direction of the planet's rotation, a phenomenon known as a retrograde orbit. This unusual motion hints that Triton is a captured object, likely a former Kuiper belt body, dragged into Neptune's gravitational pull long ago. But if Triton could produce a sound, what would it be? And what might it tell us? Just like other celestial bodies, Triton doesn't generate sound in the traditional sense. Space is a vacuum, so sound waves cannot travel. However, scientists use a technique called sonification to convert data about Triton's orbit, surface features, and environmental interactions into audio. By listening to Triton, we can gain a deeper appreciation of its unique characteristics and extraordinary journey. Triton's retrograde orbit could be represented as a low, eerie tone, an audible metaphor for its defiance of typical orbital behavior. Its motion is gradual, completing a single orbit around Neptune every 6 days. But this steady rhythm might be punctuated by higher-pitched notes representing the gravitational tugs from Neptune's immense pull. Over millions of years, this pull has caused Triton to spiral closer to Neptune, and one day, the moon may break apart entirely, forming a ring system around the planet. But Triton's story doesn't stop at its orbit. Its surface is a frozen, alien landscape, covered in nitrogen ice and dotted with geysers that erupt with nitrogen gas. These eruptions could translate into occasional sharp whistling sounds, adding bursts of intensity to the otherwise low, rhythmic tones of Triton's orbit. This interplay of tones might symbolize the delicate balance between Triton's icy stillness and its active geological life. The moon's origins and history could also be told through sound. Triton is thought to be a captured Kuiper belt object, which means it once roamed the icy fringes of the solar system before being captured by Neptune's gravity. This dramatic change in its path could be represented as a shift in pitch, a sudden alteration in tone symbolizing its past and its transition to a Neptune-bound existence. Sonification not only captures Triton's scientific data, but also makes it more accessible. By translating its motions and phenomena into sound, researchers can uncover patterns that might be harder to notice visually. For example, slight variations in its orbit caused by Neptune's pull or interactions with other moons can be represented as subtle changes in tone, helping scientists study its structure and evolution. These auditory experiences also allow visually impaired individuals to explore the wonders of Triton and its distant home. 22. Francisco far from Earth. Discovered in 2001 by astronomers using powerful telescopes, Francisco is one of the faintest and smallest moons in Uranus's vast system. With a diameter of only about 22 kilometers, it drifts in the outermost reaches of the planet's irregular satellite family, following a retrograde orbit. a backward path compared to Uranus's rotation. While Francisco itself is silent in the vacuum of space, science allows us to imagine what its sound might be like through a process called sonification. Francisco's orbit is peculiar and chaotic. Unlike regular moons, which travel in predictable, nearly circular paths, Francisco's orbit is highly inclined, elongated, and unstable. This moon belongs to a group of irregular satellites, likely captured by Uranus's gravity billions of years ago. If its orbital behavior were converted into sound, we might hear a fluctuating and unpredictable melody. Its path around Uranus could create a wavering hum, with shifts in pitch representing changes in its distance and speed as it moves along its eccentric orbit. Adding to its unique story is Francisco's delicate gravitational dance with other moons in the Uranian system. These interactions, though subtle, influence its movement over time, creating tiny shifts in its orbit. If these gravitational tugs were represented in sound, they might resemble faint, sporadic tones, like distant chimes interrupting an otherwise steady rhythm. Francisco's origin story also adds to its imagined soundscape. Like other irregular moons, Francisco is thought to be a fragment of a larger object that broke apart in a massive collision long ago. The debris from this ancient event likely scattered, and Uranus's gravity captured some of the remnants, forming the irregular satellites we observe today. Sonifying this history could produce sharp, percussive beats, representing each collision or fragmenting event that shaped Francisco's existence. This approach isn't just imaginative, it's practical. Sonification can reveal patterns in Francisco's movement that might be missed visually, such as irregularities in its orbit or interactions with nearby moons. It also makes these distant celestial objects accessible to a broader audience, including those with visual impairments, by transforming data into something we can hear. 23. Philofrosine. Far out in the vast reaches of our solar system, among the icy moons and rings of Jupiter, lies a tiny moon named Philofrosine. This lesser-known moon, just a fraction of the size of Earth's moon, orbits its giant planet quietly, overshadowed by Jupiter's more famous companions like Europa and Io. But even in its smallness, Philofrosine holds secrets, and imagining its sound offers a fascinating way to explore its celestial journey. Philofrosine belongs to Jupiter's irregular moons, a group of small, distant moons that follow orbits tilted and elongated compared to the planet's main satellites. These orbits suggest a dramatic past. Moons like Philofrosine were likely captured by Jupiter's immense gravity after forming elsewhere in the solar system. This capture process, combined with the moon's interactions with other celestial bodies, has left its mark on Philofrosine's trajectory, making its sound more complex than it might seem. Of course, in space, sound waves cannot travel because it is a vacuum, but scientists can use a process called sonification to translate data about celestial objects into sound. For Philofrosine, data such as its orbit, distance from Jupiter, and interactions with other moons can be transformed into audible tones. Imagine this. Philofrosine's slow, irregular orbit could produce a deep, droning hum, reflecting its long journey around Jupiter, which takes almost 700 Earth days. Its occasional gravitational tugs with nearby moons might be represented by faint, sporadic high notes, like whispers from its distant companions. Adding to this celestial symphony is the story of Philofrosine's past. Its irregular orbit hints at violent encounters, perhaps with other moons or asteroids. These dramatic events, if sonified, could create sharp, percussive sounds, like drum beats that break the steady rhythm of its orbit. These noises symbolize the chaotic forces that shaped this moon's history, turning it into the solitary wanderer we observe today. 24. Charon. Charon, Pluto's largest moon, is more than just a companion to the dwarf planet. It's a world with a story as fascinating as Pluto itself. Discovered in 1978, Charon is unique in many ways. It's so massive compared to Pluto that the two don't have the typical planet-moon relationship. Instead, they orbit a shared center of gravity, or barycenter, which lies in the space between them. This dynamic makes the Pluto-Charon system one of the most intriguing duos in the solar system. But what if we could hear Charon? Like other celestial bodies, Charon doesn't produce actual sounds in the vacuum of space, where sound waves cannot travel. However, using data collected from missions like NASA's New Horizons, scientists can turn information about Charon's orbit, surface features, and interactions with Pluto into sound through a process called sonification. This allows us to listen to Charon's story in a way that engages our senses and imagination. Imagine standing on Pluto's icy plains, gazing at Charon in the sky. Its orbit around Pluto takes about 6.4 Earth days, perfectly synchronized with Pluto's rotation, so that the same sides of both worlds always face each other. This tidally locked dance could be translated into a rhythmic and steady hum, representing the constant gravitational connection between the two. The deep, resonant tones of this hum would symbolize the immense gravitational forces at play, tying the two worlds together across the void. Charon's surface adds complexity to its soundscape. The moon is covered with ice, including a reddish patch at its north pole, thought to be caused by methane escaping from Pluto and freezing on Charon. This feature, nicknamed Mordor Macula, might be represented in sound as a subtle shift in pitch or tone, illustrating the exchange of material between these two worlds. Craters and canyons etched into Charon's surface could be rendered as occasional, sharp drum beats or crackling noises, evoking the ancient impacts and tectonic forces that shaped it. The Pluto-Charon system's shared barycenter would also add a layer of intrigue. Unlike moons that orbit closer to their planets, Charon's movements create a unique gravitational rhythm, influencing Pluto in ways that could translate into complex, interwoven melodies. These interactions might resemble a duet between two celestial bodies, each contributing its part to a harmonious cosmic dance. 25. Amalthea. Amalthea, one of Jupiter's many moons, holds a special place in the story of our solar system. Discovered in 1892 by Edward Emerson Barnard, this small and irregularly shaped moon was the last one to be identified by direct visual observation rather than photography. Orbiting just 181,000 kilometers from Jupiter, closer than our moon is to Earth, Amalthea experiences intense gravitational forces and radiation from its massive host planet. While it doesn't produce sound in the traditional sense, scientists have found ways to hear its story by converting data into sound through a process called sonification. Imagine Amalthea orbiting within the intense gravitational and electromagnetic environment of Jupiter's inner system. Its irregular surface, marked by deep craters and red patches of unknown origin, reflects light unevenly, creating an almost chaotic appearance. Through sonification, data from Amalthea's surface features, orbital path, and interactions with Jupiter's powerful magnetosphere can be translated into sound, revealing a unique and complex auditory profile. The sound of Amalthea might start with a low, rhythmic hum, representing its orbit around Jupiter. Moving at about 26,500 kilometers per hour, its swift motion creates a steady and persistent beat, a reminder of its ceaseless journey through space. Superimposed on this hum could be irregular, sharp tones, representing the moon's uneven surface and the impact craters that scar it. These variations in sound could mirror the chaotic history of bombardments Amalthea has endured over billions of years. But Amalthea's story isn't just about its orbit or surface. Its interactions with Jupiter's magnetosphere add another layer to its auditory narrative. Jupiter's magnetic field is the largest and most powerful of any planet in our solar system, and Amalthea moves through it like a conductor in an orchestra. The resulting electromagnetic interactions could be converted into faint, eerie tones or bursts of sound, reflecting the dynamic forces at play. These sounds might resemble faint crackles or whispers, hinting at the invisible connections between Amalthea and Jupiter. Amalthea's internal structure also contributes to its sound. Scientists believe it's a loosely packed collection of rocks with a surprisingly low density, suggesting it may be a rubble pile held together by gravity. If this structure were translated into sound, it might produce softer, hollow notes, contrasting with the harsher tones of its external environment. This combination of sounds, steady rhythms, sharp tones, faint crackles, and soft echoes, creates a cosmic symphony unique to Amalthea. 26. Praxidike. in the vastness of Jupiter's complex moon system lies Praxidike, one of the many smaller satellites orbiting the gas giant. Part of the Ananke group, Praxidike is an irregularly shaped moon, likely a remnant of a larger celestial body that shattered long ago. While small and less famous than Jupiter's larger moons, such as Europa or Io, Praxidike holds its own story. Through the process of sonification, scientists have found a way to imagine what its sound might reveal about its place in the Jovian system. Space, as a vacuum, doesn't allow sound waves to travel, meaning celestial objects like Praxidike don't produce any noise we can naturally hear. However, by using data collected from telescopes and spacecraft, such as its orbital behavior, surface characteristics, and interaction with Jupiter's gravity, scientists can convert this information into sound. Sonification transforms the abstract into something tangible, a way for us to hear the cosmos. Praxidike orbits Jupiter at a distance of about 21 million kilometers, making it one of the more distant moons. Its orbit is retrograde, meaning it moves in the opposite direction of Jupiter's rotation, which is a clue to its origin as a captured object from the outer solar system. If we could translate Praxidike's orbital path into sound, it might resemble a low, swirling hum, reflecting its distant and steady journey around Jupiter. The retrograde motion could add a distinctive quality, a subtle echo or reverse rhythm that sets it apart from prograde moons. This small moon is part of a larger narrative. Praxidike is likely a fragment of a larger asteroid or body that was shattered in a collision billions of years ago. Its irregular shape and cratered surface tell of a violent past. If this story were turned into sound, we might hear sharp, sporadic beats, representing the impacts that shaped its surface, interspersed with longer, quieter tones reflecting its stable current state. These sounds create an auditory timeline of chaos and calm, mirroring the history of Praxidike and its companions in the Ananke group. Jupiter's immense gravity plays a crucial role in shaping the sounds we might associate with Praxidike. As it orbits the gas giant, the moon's path is influenced by tidal forces and gravitational interactions. These interactions could be represented in sound as fluctuating pitches or subtle vibrations, capturing the dynamic push and pull of Jupiter's gravitational dominance. Together, these elements would create a rich soundscape, a blend of harmony and tension that symbolizes Praxidike's relationship with its massive host planet.